when you do a physics degree, you learn a bunch of problems, and you learn to recognize patterns, and then you know, oh, I have a new problem, or this problem is closest to this one, and so I'm going to use those things, right? And this is what I find completely unsatisfying. So when I was a summer student at CERN in 1999, then I was sort of asking myself, so where I met my wife there, well, future wife, it wasn't my wife at the time, but the point was that, okay, I was studying engineering at the time. I wasn't doing physics, and I just, wanted to know, like, what are these things? I wasn't really going to read, to another thing. So I said, okay, I'm in a CERN. There's a big library, and what I'm sure that there is going to be a book, a textbook, that in the first chapter is going to tell me, oh, this is what quantum systems are, and this is why you should use this thing. And of course, I went through 20, 30 books, and I found no such.
Why didn't you ask someone?
I asked somebody. I got no answers. Yeah.
And you got no answers, or you got unsatisfactory answers?
I got the answers. Well, I don't know. I can tell you. This is beats me.
Okay, well,
above.
It obviously wasn't a great enough answer that it stuck with you.
Oh, there was no answer. Like the most professors that, all the professors that I talked to, they admitted not having an answer, and they just point me to somewhere else. Oh, Bell did some stuff. Go read that. I have no idea. And actually, the turning point for me was when a PhD student at the time told me, look, you're never going to find these answers. The only thing that we have is the math. I can teach you the math. And so he taught me the math. And I learned the math badly, like all physicists. And it then stayed there for me. Okay, why do I have that math, right? And then, okay, that's reverse engineer the math. That's sort of how physical mathematics, how reverse physics started. And then I realized, well, I need to actually understand the math a lot better, and that's why. But anyway, we're talking about quantum mechanics. So let me tell you what I think quantum mechanics is. And so the short story is this, is that classical mechanics assumes that you can take something, divide it, and you can still talk about what things are. And studying the part, all the parts is equivalent to studying the whole. So if you have a ball, you can throw the ball, look how the ball evolves and describe the ball, or you can take a red marker and put a red dot on the ball and study the motion of the red dot on the ball, right? And so studying the motion of the whole ball is equivalent to studying all the possible red dots that you could put on the ball. All possible finite sizes.
Okay.
Right, because the infinitesimal is just the limit of all the possible finite sizes. And so when you have all the possible finite sizes, although dimension, that's how you define.
Now, the reason I keep having this as a sticking point is because infinitesimal doesn't mean point. It means it's as close as you get to a point without being a point.
Right. So this opens a whole another word, is how do we define calculus? Because I don't think, when I'm doing physical mathematics, I will need to define calculus at some point. And I don't think the starting points that we have for calculus can be physically motivated. I want to have a notion infinitesimal that is similar to what, Newton used to think. And right now, if you look at the books of how differential geometry is defined, you really don't have those things. You have completely different definition that even when I talk to other mathematicians that do topology, for example, like I was at a conference, a topology conference, talking to one of the students, and I asked, why are you interested in topology? And one of the reasons that he said was because the definition of differential geometry were too abstract for him and made no sense. To a mathematician, to somebody who has a PhD student. So if they're too abstract for him, you can imagine for somebody that has a physics or engineering background. So I'm trying to understand how we can actually define things in a way that are sort of similar to this idea of pieces that become smaller, but they actually we can do it with modern math. So we would define it in a way that a modern mathematician would look and say, okay, yeah, this is rigorous. This actually works, right? But this is a whole other problem. So we're at physics right now. We don't care exactly what the infinitesimal means, but it's this intuition that you had. It's something small, but it's not zero. Because if it's zero, and then we have all points that are zero dimension, how do we get the whole again?
Okay, so getting to the bowling ball, and you can mark it with all these different points. Or
Yes.
mark it with a finite point.
Finite, but whatever size you want. So it's arbitrarily small as you can. And so at that point, it means essentially describing all the points and so on. Okay, so this is classical mechanics. And in one way or another, in all that you do in classical mechanics, you are going to have this thing. So,
oh, just a moment. Is this classical mechanics in conjunction with thermodynamics yet? Or is this just pure classical mechanics?
It's pure classical mechanics.
Okay, so we need to distinguish those two. Do you in your head call that pure classical mechanics? Or is the other one where there's the Heisenberg uncertainty analog is something more CM plus T, thermodynamics?
Yeah, so the thermodynamics enters. So this is where I cannot give you a straight answer because in my mind, the distinction is yet not clear. Because you can understand one physical thing and one mathematical thing. Physically, you can understand that if I say that what I'm really studying are objects and I'm looking at these parts and so on, there is already a sense that, well, I'm kind of doing some statistics there. So exactly what is it that I'm doing, I don't know. Is it enough to get, I see, I don't know. Okay. But what I can tell you is this, is that this is another thing that I think, we look at it backwards. We think as statistical mechanics and thermodynamics as something that you add on top of both classical mechanics and quantum mechanics, right? So there is mechanics, which is the real thing, and then you do statistical mechanics, thermodynamics, it's all a sort of the derivative thing. It's not really fundamental. But here's the thing. As I said, remember that count of states that we need to define to have classical mechanics, classical Hamiltonian mechanics. Well, that's the geometrical structure of classical mechanics. It's these symplectic forms that allows you essentially to count the configuration, to count the states. Okay, so that thing is what you use then to calculate thermodynamic entropy. So you use that structure to calculate the entropy. Now, if I gave you all possible distributions, probability distribution in phase space, and I told you what was the entropy of all those distributions, like the Shannon entropy, Gibbs entropy, you would be able to recover the symplectic structure. So the symplectic structure and the entropy are equivalent because either I give you one and you can calculate the other, or I give you the other and you calculate the first one.
Interesting.
So the geometrical structure of classical mechanics is exactly the structure that you need to be able to do thermodynamics and statistical mechanics. So how can you say that one is built on top of the other? They're really one unit. The same applies for quantum mechanics. The geometrical part of quantum mechanics is given by the Born rule. The inner product tells you what is the probability from going from one state to another state during measurement. Okay? You use the Born rule to calculate the von Neumann entropy, the entropy of distribution. Now, if you take all distribution, in fact, if you take in particular the uniform distribution over two pure states, and you look at that entropy, from that entropy you can recover the probability of transition from one to the other. So again, I could give you the geometric inner product structure of quantum mechanics, and you can recover the entropy. Or I can give you the entropy, and you can recover the inner product. They are equivalent. So again, how can you tell me, oh, quantum statistical mechanics is something that we sprinkle on top of quantum mechanics? They're really much more tied in. So that's why I can't make this argument fully, because again, this is where I said I need this theory of ensembles. I need something that is more foundational to be able to say why I have these things, how exactly they are related or not.
Don't forget to follow Theories of Everything with Curt Jaimungal on Spotify for exclusive content and in-depth discussions. Your support on Spotify helps us grow and to reach more curious minds like yours. Check out the link in the description and join the Core Toe community on Spotify today. See you there.